So, before John Dalton and Dmitri Mendeleev, one of the most notable ancient classical philosophers named Democritus theorized the atomic theory. He said, "Nothing exists except atoms and empty space. Everything else is opinion." Learning about the makeup of atoms is important because they are the fundamental building block to our universe. Sit back and enjoy a Chemistry Uncovered special, Tutoring in Atoms Electron Configuration. Hey guys, Chemistry Uncovered here. Before the electron configuration tutoring video starts, I just want to say thank you so much for 100+ subscribers. That means so much for us, for me, and the Chemistry Uncovered team. And we will use this as motivation to continue to upload state-of-the-art chemistry content. Not only chemistry, we are also thinking about expanding to physics. So comment down below if you guys want to see that. And also, this summer, you guys are going to get an exclusive look at interviews at labs and, better yet, chemistry tutoring content. So make sure to subscribe if you haven't already, because 60% of you guys aren't subscribed yet. Make sure to turn on your post notification bell, and thank you for supporting. Enjoy the video. Peace out. Now, you may be asking, why are we even learning electron configuration? Now, in order for us to understand why we learn electron configuration, I think we have to take a deeper dive into the quantum mania, quantum chemistry that we taught a couple weeks ago, right? To synthesize, electron configuration uses quantum numbers and mechanics in order to explain how electrons are situated in their respective atoms, but not only atoms, more deeply into the shells. And not only shells, but their subshells, right? Knowing where electrons are located in an atom helps us with valency and bonds, with structure of atoms, with periodic trends, with effective nuclear charge, and much more. Okay, so hey guys, well, before we get into how to write electron configuration notation, I think it's pretty important to talk about some of the principles that the electron configuration notation has. The first principle being the Aufbau principle. Essentially, the Aufbau principle states that electrons fill lower energy atomic orbitals before filling higher energy atomic orbitals, right? This is obviously because electrons tend to try to attract to the nucleus closer and to be the most stable, which means they have the lowest energy. This also means that following the Aufbau principle, the electrons fill the principal quantum number of n equals 1 before the principal quantum number of n equals 2, then n equals 3, right? And so the second principle is the Pauli exclusion principle. This principle states that no two Fermi ions have the same magnetic spin. Essentially, for every orbital, there's 2 electrons, right? But in those 2 electrons, one electron has a positive half magnetic spin, one electron has a negative half magnetic spin. And the reason why I put the Fermilab logo in the bottom is because this is a national institution that is a trailblazer in nuclear chemistry and nuclear science. And the Fermilab name was actually inspired by Enrico Fermi, who also created the Fermi ions. And then the third principle is the Hund's rule. The Hund's rule, there's 2 main rules. The first one states that every orbital is singly occupied with 1 electron before it's doubly occupied. Essentially, this means that if we have the subshell of P, since there's 3 orbitals, right, the first 3 electrons fill 3 different orbitals of positive magnetic spin before the next 3 electrons fill those 3 orbitals to fill all the orbitals with 2 electrons with a negative magnetic spin. And the second one just basically restates the first rule, which says that all electrons that are singly occupied have the same spin in order to maximize the total spin which electrons prefer. And then now we're going to get into the meat and bones of writing electron configuration, right? So the three main portions of the electron configuration notation is the energy level, which looks like a coefficient, the number 1 in this case, the subshell, which is a letter, and then the number of electrons, which is a superscript, right? And so to start off, in the energy level is also commonly known as an atomic subshell. Energy levels correspond to the principal quantum number. I'm sorry that is blocked, but it is the principal quantum number. So if the principal quantum number n value is 3, then the energy level is 3. For subshells can either be S, P, D, or F. The subshell corresponds to the angular momentum quantum number, the L value. If you guys need a refresher on the quantum numbers, go back to our previous video about quantum chemistry and quantum mania. But to kind of debrief, when L equals 0, that means that it's the S subshell. When L equals 1, the P subshell. When L equals 2, the D subshell. And when L equals 3, the F subshell, right? Last but not least, electrons and orbitals. Now this one's the most complicated one, so bear with me before we actually start to do practice problems. So I hope you guys stay long enough for this. So for this one, the number of orbitals for each subshell corresponds to the number of magnetic quantum number per L value. Essentially what this means, I know it's very complicated, it looks very sophisticated and complex, but to boil it down to simplistic terms, what it means is when the L value is 0, the ML value is 0, which means that there's only one orbital and 2 electrons. When the L value is 1, the ML value can equal -1, 0, or 1, which means there's 3 orbitals. So for however many ML values there are, that's however many orbitals there are. And to find the total electrons, you just do the orbitals multiplied by 2. And then, so basically S has 1 orbital, since L equals 0 corresponds to ML is 0, and it also corresponds to 1 orbital. P has 3 orbitals, D has 5 orbitals, and F has 7 orbitals. So when we write the notation, keep this in mind. I have a table right here, so keep this table in mind. Take a screenshot of this because we will do practice problems soon, and this is kind of a debrief on what I was talking about the rules, and then also the N value, L value, ML value, and magnetic spin. For example, in the N equals 2 shell, there's an L value of 0 and 1, right? When the L value is 0, the ML value is 0, which means the number of orbitals is 1 and 2 electrons. When the L value is 1, the ML value is -1, 0, 1, which means there's a total of 3 orbitals, and there's a total of 6 electrons, which means in total there are 4 orbitals and 8 electrons. Same concept goes for the 3rd subshell, the 4th subshell, and the 1st subshell. So I hope you guys enjoy the practice problems that we will do next. Hey guys, so now that we covered the electron configuration principles and some of the background information, such as the notation of what even is 1s2, right? Now this is the energy level, I'm gonna notate that as EL. This is the subshell, I'm gonna notate that as SS. And this is the number of electrons, I'm gonna notate with electrons as an anion with a negatively charged, right? So, next, how do we write the electron configuration for, let's say, fluorine, right? If we were to write the electron configuration for fluorine, pause the video and try to write the electron configuration for fluorine without my help. So, to write the electron configuration for fluorine, what we have to do is that first we have to notice that, let me zoom in real quickly. First we have to notice that, look at my laser pointer, these 2 columns is the S block, right? These 10 columns is the D block. These 6 columns is the P block, and these 14 columns is the F block, right? So I'm going to write S, D, P, F. Now you may be asking why 2 columns is the S block. Well, that's the total number of electrons. That's the total number of electrons that the S subshell can have. So S can have 2 electrons, P can have 6 electrons, which is why P has 6 columns. D can have 10 electrons, which is why D has 10 columns. F can have 14 electrons, which is why F has 14 columns, right? So when we write the electron configuration for any element, I can't restate that enough, for any element, you go from left to right. So first, what you do is, for fluorine, it's 1s2. You always go from left to right. So you go lithium and beryllium first. That's 2s2. And then since there's no D block for in the second row, you just go straight to P, just 2p6. However, since it's fluorine, is the P subshell for the second energy level fully filled? No, it only has 5 electrons. So that means that if you got this right, the electron configuration is 1s2, 2s2, 2p5, right? Now that's electron configuration. For electron configuration diagram, I'm going to go over how you do that, right? So for fluorine, let's take fluorine for example. We already know there is 1s2, 2s2, 2p5. But how do we write that in a electron configuration diagram? Well, 1s has the lowest energy level, so we are going to do an xy coordinate, right? X meaning the subshell, Y meaning the energy of electron. For 1s, there's only one orbital, but it's fully filled. For 2s, it has a higher energy. There's one orbital, it's fully filled too. Now for 2p, this is interesting because 2p has 3 orbitals, so we draw 3 underlined dashes. But there's 5 electrons. So using the Hund's rule and the Pauli exclusion principle, we know that we have to fill these with 3 positive magnetic spins first before we do anything with the negative magnetic spins, before we fill in all the orbitals again. Since it's 5, you only do 2 more electrons. 1 arrow equals 1 electron, and this is how you do the electron configuration diagram for fluorine. And so, as I will continue to end every single video saying, I hope you guys enjoyed this video. I hope that this video could help you guys fuel your passions of chemistry and furthermore make the world a better place, okay? Please do your part in making the world a better place and using the electron configuration knowledge you guys learned, gaining chemistry knowledge, and I'm sure a bunch of new knowledge that you guys gain every single day. Please make this world a better place, and that's the end mission of Chemistry Uncovered. This has been Chemistry Uncovered episode 15. I will be back next week with another banger, so peace out.